In this video, we'll go through some examples using U substitution, sometimes called the reverse chain rule. Integrate cosine 3x dx. We know that the integral of cosine of a single variable is the sine of that variable, so we can make this integral easier by replacing 3x with a single variable. We'll call that variable u and say that u equals 3x. Rewriting gives us the integral of cosine of u. But if we make that substitution, we need to integrate with respect to u, not with respect to x, so we need to replace dx with an expression involving du. To find this expression, differentiate u equals 3x with respect to x on both sides, getting du dx equals 3. Then multiply both sides by dx, getting du equals 3dx. We can add this to our list. It turns out that this step always gives us something that looks like this, where we have du equals whatever the derivative of the right side is with a dx tacked on. Solving this for dx is what allows us to replace dx in our integral. In this case, we have dx equals 1/3 du, and then substituting that into our integral gives us the integral of cosine of u times 1/3 du. Once we move our constant out front, we get an integral of the same form that we were looking at in the beginning that we wrote at the top in green. Following that example, integrating gives us 1/3 sine of u. Our solution needs to be in terms of x and not u, so the last step is replacing u with our original expression 3x, giving us 1/3 sine of 3x. Because this is an indefinite integral, we add a plus c for our constant of integration. Integrate x e to the negative x squared dx. Now there's a few things we should notice before starting. The first thing is that the integral of e to some variable is just e to that variable. Because of how simple this is, it would be nice if the negative x squared in our integral was just one single variable as well. The other thing we should notice is that x and x squared both appear in our integral. When we have two instances of the same variable with consecutive powers like this, it usually means we take an inside function that involves the variable to a higher power and call that our u. We'll see the reason for this soon. Let's just say that these two observations indicate strongly that u should equal negative x squared. Substituting that into our integral gives us the integral of x e to the u. To replace dx, we follow the same process as the last problem. We differentiate both sides of u equals negative x squared with respect to x, and then multiply by dx, giving us du equals negative 2x with a dx tacked on. Then we solve for dx, getting dx equals negative 1/2x du. Substituting this for dx gives us the integral of x e to the u times negative 1/2x du. Now you can see that by including the higher power of x in u and then differentiating, an x has found its way into the denominator of our integral, allowing us to cancel out both x's. This leaves us with the integral of negative 1/2 e to the u du, which we can solve. Moving our constant out front gives us negative 1/2 times the integral of e to the u du. From our notes at the top in green, we know that integrating gives us negative 1/2 e to the u. The last step is replacing u with our original expression negative x squared, giving us negative 1/2 e to the negative x squared. Because this is an indefinite integral, we add plus c for our constant of integration. Integrate x to the third times the square root of x to the fourth minus 4 dx. Anytime we have a radical in our integral, we should consider what's underneath the radical as a candidate for u. That's because the integral of the square root of a single variable is known to us. We also have an x to the third and an x to the fourth in our integral. Just like in the last example, this is a variable raised to two consecutive powers, meaning we should consider an inside function with the higher power of x to be u. Both of these things indicate that we should try u equals x to the fourth minus 4. This substitution gives us the integral of x to the third times the square root of u. To replace dx, we differentiate both sides of u equals x to the fourth minus 4 and multiply by dx, giving us du equals 4x to the third dx. Solving for dx, we get 1 divided by 4x to the third du. Together, this gives us the integral of x to the third times the square root of u times 1 divided by 4x to the third du. The x's cancel, leaving just the integral of 1/4 times the square root of u du. We first move our constant out front and then use the fact that we wrote in green, integrating to get 1/4 times 2/3 u to the 3/2. Simplifying gives us 1/6 u to the 3 halves. The final step is replacing u with our original expression, giving us 1/6 times x to the 4th minus 4 to the 3 halves. We can then add our constant of integration. Integrate sine squared theta cosine theta d theta. In some problems, it's less obvious what to choose for u, and we might need to try a few different values. You'll know if you choose the wrong value for u, because either the integral will become more challenging or nothing will cancel out after substitution. First, I'll demonstrate a few incorrect values for u, followed by the correct one so you can see the difference. So here are a few incorrect values for u. If you want to pause here, you can take a look at them. You can see that in the first one, I chose u equals theta. This is useless because replacing the independent variable with another gives us the exact integral we started with. The second two examples end up leading to integrals in terms of both u and theta, and we need the integrals to be entirely in terms of u. So let's instead choose u equals sine theta. Differentiating both sides with respect to theta and multiplying by d theta gives us du equals cosine theta d theta. Solving for d theta gives us 1 divided by cosine theta du. Substituting this gives us the integral of u squared cosine theta times 1 divided by cosine theta du. The cosines cancel, leaving us with the integral of u squared du. We know we chose the right value for u because we have an integral entirely in terms of u now. Integrating gives us 1/3 u to the 3rd, and replacing u with our original expression gives us 1/3 sine cubed of theta. Then we just add plus c for our constant of integration. Integrate x to the 5th divided by x to the 6th minus 8 dx. We have two consecutive powers of x again, and by now we know that this means we choose x to the 6th minus 8 to be our u. Differentiating with respect to x and multiplying by dx, we get du equals 6x to the 5th dx. Solving for dx gives us 1 divided by 6x to the 5th du. Making the substitution gives us the integral of x to the 5th divided by u times 1 divided by 6x to the 5th du. The x's cancel, leaving us with the integral of 1 divided by 6u du. Moving the constant out front, we get 1 divided by 6 times the integral of 1 divided by u du, which is a common integral. So integrating gives us 1/6 ln absolute value of u. The last step is replacing u with our original expression, giving us 1/6 ln absolute value of x to the 6th minus 8. We now add our constant of integration. Integrate ln x quantity squared divided by x dx. In this example, we use the fact that the derivative of ln x equals 1 over x in order to cancel out our denominator. Let's see how this works. Set u equal to ln x. Differentiating with respect to x and multiplying by dx gives us 1 over x dx, and solving for dx gives us x du. Substituting this back into our integral, we have the integral of u squared divided by x times x du. Now we can cancel our x's and we're left with the integral of u squared du. We know how to integrate this, and we get 1/3 u to the 3rd. To finish, we replace u with our original expression, and we have 1/3 ln x to the 3rd plus c. Integrate 1 plus x divided by 1 plus x squared dx. This integral is interesting because it's going to require some algebraic manipulation. Before we get there, let's try it out and see how we get stuck. We see two consecutive powers of x, so I don't even need to tell you that we should try u equals 1 plus x squared. Following our normal routine, we have du equals 2x dx and dx equals 1 over 2x du. But when we put that back into our integral, nothing cancels, and we still have an integral in terms of two separate variables. So did we make the wrong choice of u? As it turns out, no choice of u could have worked here without first doing some algebraic manipulation. Sometimes it's necessary to rewrite our integrand to more easily work with it. So taking a look at our integrand, we have 1 plus x divided by 1 plus x squared, which is the same as 1 divided by 1 plus x squared plus x divided by 1 plus x squared. Let's rewrite our integral. We also have a rule of integration that says the integral of the sum of two functions is equal to the sum of the integrals of those two functions. Here we say f of x equals 1 divided by 1 plus x squared, and g of x equals x divided by 1 plus x squared. Then we can rewrite our integral as the sum of the integrals of f of x and g of x. The integral of 1 divided by 1 plus x squared is a common one, and so we know it's the inverse tangent of x. The integral on the right can be evaluated using the same value for u that we picked earlier. Substituting this back into the integral gives us the integral of x divided by u times 1 divided by 2x du. The x's cancel, leaving us with the integral of 1 divided by 2u du. Moving the constant out front gives us 1/2 times the integral of 1 divided by u du, which we know to be 1/2 ln absolute value of u. Replacing u, we have 1/2 ln absolute value of 1 plus x squared. Notice though that 1 plus x squared is always positive, so there's no need for the absolute value symbols. We can just use parentheses. Our full solution is the inverse tangent of x plus 1/2 ln 1 plus x squared plus c. Integrate the square root of cotangent of x times cosecant squared of x dx. Now if you ever see a bunch of trig functions and you don't know where to begin, look for other clues. We know that when we have a radical, the expression underneath can sometimes be a good place to start. Let's set u equal to cotangent of x and see if our trig disappears. Following our normal routine gives us du equals negative cosecant squared of x dx, and dx equals -1 divided by cosecant squared of x du. Substituting this back, we get the integral of square root of u times cosecant squared of x times -1 divided by cosecant squared of x du. All of the trig disappears, and we're left with the integral of negative square root of u du. We move the constant -1 out front, and then we integrate, getting -2/3 u to the 3/2. Replacing u, we get -2/3 cotangent to the 3/2 of x. Then we just add our plus c. Integrate e to the 1 over x divided by x squared dx. There are a few definitive statements we can make about this right away. U is not x squared. This is because no amount of differentiating a polynomial term like x squared is going to allow us to cancel out an exponential e to some power. They take different forms. We can also say that u is not e to the 1 over x. This is because e to the x is a derivative of itself, and the derivative of e raised to some expression of x is found using the chain rule. This results in an expression involving the very thing we took the derivative of. If you look at this example, you'll see that there's still an e to the 1 over x in the denominator, even after substituting the other e to the 1 over x out for u. Instead, let's set u equal to 1 over x. I rewrote this as x to the -1 for convenience. Then du equals -x to the -2 dx, and dx equals -1 divided by x to the -2 du, which I'll rewrite as -x squared du. These substitutions give us the integral of e to the u divided by x squared times -x squared du. The x's cancel, giving us the integral of -e to the u du. We move the constant -1 out front and integrate to get -e to the u. Replacing u with our original expression, we get -e to the 1 over x and add our constant of integration. Integrate dx divided by x times the square root of ln x. First, let's make an aesthetic choice and get rid of this dx by moving it off to the side as the integral gods intended. Then we'll make the usual guess that u will be the expression under the radical, so u equals ln x, du equals 1 over x dx, and dx equals x du. Making these substitutions, we get the integral of 1 divided by x times the square root of u times x du. The x's cancel, giving us the integral of 1 divided by the square root of u du. Although this form is unfamiliar, we can rewrite it as the integral of u to the -1/2. This is just a variable raised to a power, which is something we certainly know how to integrate. We add 1 to the exponent and divide it by the new exponent. This gives us u to the 1/2 divided by 1/2, which is the same as 2u to the 1/2. Replacing u with our original expression, we have 2 times ln x to the 1/2. For preference, I like to write exponents of 1/2 as square roots, so this becomes 2 times the square root of ln x. Then we just add our constant of integration.